Now in this section we shall learn about derivation of centripetal acceleration. Now centripetal, this word actually means center seeking. That means something directed towards center of a circle. Since we have got some basic knowledge about circular motion, we have told earlier that circular motion can be of two types. In uniform circular motion, the particle has got constant speed, that is constant angular velocity, and in non-uniform circular motion, the angular velocity of the particle keeps on changing. Now if we consider the easier case, the uniform circular motion, then we see that the speed of the particle remains constant throughout, but then the velocity vector is changing because there is a change in direction of the velocity vector. Let's see this. So first of all, I shall construct a diagram and show the circular motion of a particle like you can see here. This is a circular path and this is my coordinate system, where I make sure that the origin of the coordinate system coincides with the center of the circle described by the particle. So here I just name this as usual, that is x-axis, and this is y-axis, and they meet at the origin O, that is also the center of the circle described by the particle. This is the path of the particle. And suppose the particle at initial time t1 is at this location. Now that is I call p1 the initial location, and the time is t1. This time is t1, and at this moment you know that the position vector of the particle is given by simply OP1. This is, I'm just joining O, that is the origin, to the location point P1 where the particle is, and after some time, say at time t2, the particle has gone along the circular path and its new location is of course now P2. This I show here. Now this happens at the time t2. So you see that what I have drawn in this case, as the particle has traveled from position P1 at time t1 to position P2 at time t2, correspondingly the position vector of the particle, now that's given by this OP1 is the initial position vector of the particle. Now this I'll be calling R1 vector, and later it has gone to OP2. Now that I shall call the R2 position vector. So it has changed from R1 to R2. Initially, position vector of the particle was OP1, we call that R1, and then it has gone to OP2, and that we called R2. So it has changed. And incidentally, you must note that although R1 and R2, they are two different vectors, but their magnitudes, we can use this symbol here, R1 modulus symbol, and that it must be equal to the modulus of R2 vector, because both of them are the same, and that we can call R. Actually, you can use even an easier symbol, a simpler symbol, that is just R1 is equal to R2, and both of them are equal to the radius of the circle, because that is not changing. So we see here R1, R2 are different vectors because they have different directions, but their magnitude part, that are the same, which is equal to the radius of the circle described by the particle P. Now what we need to note here is that even if the motion is uniform circular motion, which means the angular velocity or linear speed of the particle remains constant, we cannot say the same for the linear velocity of the particle. Why? Let us say this. See, at the initial time, that is at time t1, this when it was at point p1, the velocity vector was pointing along this green arrow, and that we could call the v1 vector. And when it has gone to this position P2, even though the speed has remains constant, which means the length of the green arrow remains constant, but direction has changed. As you can see, everywhere velocity is given by its direction is given by the tangent drawn to the circle at that point. So while at P1, you draw this tangent direction, and there the V1 is directed, and later it has gone to P2. There you again need to draw a tangent, and you found that direction of velocity vector has changed. So we might call these two vectors as V1. The initial position was P1, I call it V1, Later it has gone to v2, and that velocity vector is called v2. See once again that I could write down the v1 velocity vector is not equal to velocity vector v2 because they have different directions. But since we said that the linear speed remains constant, so we could say that the magnitude of v1, which you can call also simply v1, and magnitude of v2, the other velocity, these two things must be the same, and let me call that as v. I have said we could use a simpler symbol, and we shall stick to that simpler symbol in future. That is just like writing v1 is equal to v2 is equal to v. Now this was my question number 1, this is my question number 2, which show that vectorially the position vectors have changed from r1 vector to r2 vector, from op1 to op2 because of change in direction. But the magnitude of r1 and r2 are the same, which is equal to the radius of the circle. Similarly, as the particle travels anticlockwise, the speed, the v has remains constant for both the positions, or for that matter anywhere along the path, because we consider here uniform circular motion, but the velocity vectors v1 and v2 are different because they have different velocities along the tangents drawn at those particular points. Once we appreciate that velocity vector has changed from v1 to v2, although their magnitudes have remained same, it is easier to grasp the meaning of centripetal acceleration. Since in uniform circular motion, the velocity is changing although the speed is remaining constant, we can define an acceleration as follows. Like we can write down, this is a vector, that is acceleration, and the average value of that acceleration can be defined to be, you are aware that is change in velocity vector. We are talking about motion in a plane, so you must be using the vector symbol. Delta v, that is v standing for velocity vector change, divided by change in time considered, and that could be written as the velocity vector final minus velocity vector initial, v2 minus v1, that's a vector subtraction, divided by final time is t2 and initial time is t1. Now this what we have written on the board, on the screen, that is the average value of acceleration due to the change in velocity from p1 to p2 over the interval t2 minus t1. This symbol, the bar symbol, means we are looking for the average value of the acceleration caused by the change in velocity, but that again because of change in direction only. The magnitude part of v did not change. At this point we shall make a construction because we have to really explore this vector subtraction. The most interesting part here about this expression is that here we have got a vector subtraction, v2 minus v1. This is not a simple arithmetic subtraction like 5 minus 3 or 10 minus 2. It's a vector subtraction because the crux of the problem is both v2 and v1 have the same numerical value. Maybe they are both 5 meters per second. So numerically they are same. But why they are different? Because they have different direction. So we must learn and apply the practice, the method of vector subtraction here carefully, which requires little bit of elaboration. As you can see, I have done a construction here. These velocity vectors v1 and v2, they are free vectors in the sense that they can be shifted on the screen, on the board here, anywhere, keeping their lengths and directions intact. That is, you can see this was v1, and of course v1 and v2 having same magnitude, it means that they have the same length, only directions are different. And similarly, r1 and r2 vectors, these arrows have the same length because they have the same magnitude, only direction is variable. So suppose I say the angle between r1 and r2 vectors, these position vectors, is delta theta, I call it. That is the angular displacement of the particle as it travels from p1 to p2. So what we have done is that we have first just drawn this v1 here as well. You can see this is my v1 vector because I have just shifted it from here from here to here, keeping its length intact and also keeping it parallel to itself. Similarly, the v2 vector has been shifted down here. Let me write this. This is my v2 vector, because this vector and this one, you can see they have the same length, same parallel direction. They have been just shifted to make sure that their tails are meeting. Now this is a perfectly legitimate practice with free vectors, as we have done. A vector's effect remains unchanged provided we just keep its length and directions intact and shift it on the plane of the paper like this. So you have drawn v1, v2 here, right? Now similarly, we can see that on the right hand side of the screen, you have got this r1, which I have drawn here only. We have maintained the same length and same direction, just drawn parallel to itself, shifted. So I could call this one.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one, covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.